All right. Redox is, well, we talk about redox chemistry being, it is about reduction and oxidation. And I mean, all chemical reactions will fall into, either reduction or oxidation when you look at the movement of electrons. But what we're using this for is, there's another aspect to this, and it's looking at whether reactions will actually happen or not. It's all very well sort of looking at equilibrium, sort of we've just done, where does a reaction reach that balance point between the rates? And before that, we'd looked at the rates of reaction, and obviously from that, we are aware that some rates are very much faster than others, but they still happen. Along the way, we've considered things like the activation energy as being a barrier that you have to get over before a reaction will actually occur. But there are reactions that sometimes just won't happen. Because of the energy status of your reactants, they won't happen, or they will happen very easily. And so we describe this as feasibility. All right, so it's redox. And the sort of attachment to this is feasibility of reactions, let's say. Okay, so that sort of covers the whole of the learning outcome 3, really. And it's it's an overview that's, it doesn't go into a lot of depth, but it gives us one way of determining from these sort of measurements whether a reaction's feasible. Doing it practically, well, you'll see the reaction happening anyway, so you'll know the reaction's feasible. But in terms, energetic terms, really, it's going to look at that. The recap, the things that you really need to be familiar with on this are, I suppose, and I'm not going to spend ages going through these. It's just that if you don't understand these things properly, then you will find this difficult. And, in terms of sort of chemical literacy, I suppose, just in terms of being able to use the right language, the right descriptions of what's happening and all that. I would start here with understanding atomic structure and the nature of electrons. Where are they and what are they doing most of the time? So electrons, how many are there on the outside of an atom, any given atom, working out the electronic structures, the configurations, that sort of thing. So what sort of ions might they form? So it's, the atomic structure generally. To ions, whether those are positive or negative ions. All right, so think, go back to ionic bonding. So, for example, all those metals in group 1 have one outer electron, which is very easily lost, so they form a 1+ ion, don't they? Whereas the halogens all are missing one electron from a full shell configuration, so they will easily gain one, and so on. All right, that, being familiar with all that is very useful. Other things that sort of go with that, I guess, it's that idea of electronegativity. And then, generally speaking, the idea of, what's a reaction? We've looked at a huge variety of reactions in one way or another, some theoretically, some practically. But understanding what's going on there is something else altogether. Now, just to add a bit of entertainment to the afternoon, we'll start with a demonstration, I think. All right, so if we put lithium in water, we get hydrogen gas and lithium hydroxide. Similarly, you know, you could just replace the lithium with sodium or potassium. Same thing, you'd have the same reaction going on. With the water, you get the hydrogen. It becomes more obviously burned off, particularly with the potassium. And you get the lithium hydroxide. So we ought to balance that, I suppose. How should we balance that? Yeah, we can either put a 2 there, a 2 there, and a 2 there. We could have put a half for the H2, couldn't we? It is an option sometimes. It's not unreasonable because we're talking about molar quantities, so fractions are fine. So what is actually happening here? In what form is the lithium when it's a metal? It's a solid made up of atoms, right? So the lithium as a solid is atoms. Atoms are neutral, aren't they? There's no charge on an atom. And we actually know, I mean, that's not 100% true, is it? Because in metals, you have the metallic bonding, where all the electrons are shared. You get that sea of electrons. You get the delocalized electrons all going around. But let's assume that a metal is made of atoms. You know, if you cut it down to its smallest amount, you'd have an atom. So we have no charge on the lithium at all. The water, we know, is a molecule, and it's a covalently bonded molecule. Again, no charges. On the other side, we've got a hydrogen molecule, no charges, and lithium hydroxide. Now, because we're working in water, then that's going to be dissolved. So what form is the lithium hydroxide going to be in? Sorry? Well, it is aqueous, which means what about the lithium hydroxide? Ions, yeah. So if we follow the lithium, this will get a little bit messy, but if we were to just look at the lithium, we start with 2 atoms. Oh, I didn't know I was in red. Over this side, and over that side we've actually got 2 what? What am I going to put on that? Li, what's happened to it? Plus, yeah? It's in group 1, so it's lost a single electron, yeah? Now we have to sort of account for those electrons, and this is what redox chemistry is all about, you know, where are the electrons coming from and going to. And as far as the lithium's concerned, then it's actually lost an electron. That actually means it's been oxidized. Oxidation is the removal of electrons, but we'll do all the definitions a bit later. We've got, you know, work our way up to that. But we are removing electrons, and so we could write, but this is not how you do it, you could put 2Li minus 2 electrons gives you 2 lithium ions, but you've sort of then lost the electrons. So we don't actually write it like that. All right, instead of that, we put them on the other side. We always do plus, because then we've still got everything. And that is a very simple little part of a redox equation. All right, looking at what's happened to the lithium. It's gone from being an element, an atom, to an ion that has lost the electrons, and the electrons are available. Now, following the rest is not quite so easy. If you think of, I'm not quite sure how I'm going to do this actually, the rest of it, but the water has been reduced, really. The water, the O and the H have picked up an electron. So how am I going to write this? I think the only way I could do it, just for the sake of completeness, is if we take what we've got over here, if we add 2 electrons on this side, what we can then make out of this is our H2, and what will be the other thing that I will need to write? So, not OH2 minus, but you're close. It's OH sorry, no, 2OH minus. I pointed to those in the wrong order anyway, didn't I? So, all right, so we have, that looks like 20H minuses. Yeah, something to be a little bit careful of, isn't it? And it's not a very good equation, that one. But that's, that is actually what's going on in that reaction. Now, I suppose the nearest we've come to this so far was the reaction that you did in the rates bit, the thiosulfate one, where the thiosulfate ion actually produced the sulfur, didn't it, and sulfur dioxide. I'm trying to think what else we had out of that. But there were two ions in that reaction that we completely ignored. I don't know if you can remember. Sodium and chloride, yeah? Because you were reacting sodium thiosulfate with hydrochloric acid. And we ignored the sodium from the sodium thiosulfate, and we ignored the chloride from the hydrochloric acid. And I described them as spectator ions. Now, in the sense of redox, this makes a lot more sense. It's because they don't change their charge. They don't gain any electrons. They don't lose any electrons. Now, I'm going to attempt to write that equation without referring to anything, which is probably a little bit risky, but we had, it was Na2S2O3, wasn't it? And the hydrochloric acid I can do, and then we had sulfur and sulfur dioxide and water and sodium chloride, I think, mops it all up, doesn't it? But within that, here, this is just a couple of sodium ions. I haven't balanced this. I suppose we should do that for the sake of completeness, shouldn't we? So I want a couple of those. That would mean I want a couple of those. And is that it? I've got something right. What a... Two S's on the left, two S's on the right, three oxygens. I think we're all right, aren't we? But these, we've got two Na pluses here. And what we've got over here, of course, is two Na pluses. So they don't get involved. They don't actually do anything. They're not reduced. They're not oxidized. They don't gain electrons. They don't lose electrons. So they're not considered as part of the reaction. Similarly, of course, you've got your two chloride ions here. We ignored those because they also just end up as two chloride ions over here. So this is why we call them spectator ions. So we reduced our equation down to just the thiosulfate because that doesn't exist over the other side, does it? It's got completely changed. We had our two hydrogen ions, because that changes. We don't have any hydrogen ions on the other side. And then the sulfur, the SO2 and the H2O are all in different forms. They've all gained or lost electrons. And so, you've got the real bare bones of a reaction looking at it that way. Okay, so that's it's just a recap on things that we've done before in order to sort of build the idea of redox. Now, we could take this last one and split it into two halves. We're going to be doing quite a lot of that, though. I'm not going to do it yet, but you could take the thiosulfate and look at that on its own, like I did really with the lithium one that we just looked at. You can do what we call half equations, and building a redox equation from half equations is going to be the first thing we do, and then we'll look at the practical work of it and the calculations that go with it. So let's start with some definitions of oxidation and reduction. I think be the next thing I want to do. All right, we're going to start with some definitions, just to clarify the different ways of looking at oxidation and reduction And we'll have three separate definitions, really. One involving oxygen, one involving hydrogen. But ultimately, we need to be able to define in terms of movements of electrons. So let's oxidation and reduction definitions. Sometimes it helps to think about the hydrogen and oxygen versions of it. I mean, when we were going through respiration, for example, it's more obviously there to do with oxygen being used or hydrogen being transferred, isn't it? However, of course, at the end you have the electron transport system. And what goes on in the electron transport system? Oxidative phosphorylation. So you can see, I hope, how, you know, this is all sort of, you know, all starting to fit together. Right, let's start off then with the oxygen approach. I mean, it's, you know, we've got respiration, photosynthesis, burning is another obvious one. You know, it crops up all over the place. You know, we talk about things being oxidized, don't we? And yeah, so here we go then. Right, first one is the oxygen-based definition. Now, it's not exactly difficult to work out then that oxidation is probably to do with adding oxygen. that's reasonable. Now, the other thing that we're going to find with this, of course, is that whenever something's oxidized, something else has to be reduced. Yeah. So the two things are just reverse processes, really. And an oxidizing agent will be reduced itself, and a reducing agent will be oxidized. So that can actually get very, very confusing, you know, trying to work out which one is the agent or which one is being affected and what happens to the agent. So, yeah, just take care with it, really. We don't use these sort of definitions generally now, but they can help. And oxidation, fairly obviously, was going to be addition of oxygen, whereas reduction would be loss. So oxidation would be addition of oxygen, whereas reduction would be loss of oxygen. All right, now if we wanted some examples, then we would have, I'm just going to use the ones in front of me because otherwise I'll end up using the wrong ones. Let's say, no, actually I'm going to use one where we've got both going on very, very clearly. And this is something that I think we've met this one before in various roundabout ways, extracting iron from iron ore. If you start with Fe2O3, which is iron 3 oxide, and you heat it up with carbon monoxide, and this is what happens in a blast furnace. You get the iron that you're actually looking for, and carbon dioxide as a waste product, if you like. So, where's the oxidation happening? What's having oxygen added to it? Yeah, the carbon monoxide is having oxygen added to it. So here's our oxidation. And so at the same time as that's happening then, something is losing oxygen and being reduced. What's being? The iron oxide, yeah. So that is the reduction. All right, but I've chosen, that one because it's specifically involving oxygen. You don't have to work out anything to do with the electrons, anything to do with ions. If we were going to, then, well, we've got iron ions over here. Each one of those Fe's in that Fe2O3 is Fe3+. And they go from being Fe3+ to Fe. So they must gain 3 electrons each, mustn't they, to cancel out those 3 pluses. So they're gaining electrons. And that's a definition of reduction. Not so easy. I suppose it's the carbon in the carbon monoxide there, going from a carbon. It's not really, because it's I don't want to give you the impression these are ions, but it's almost like it's going from carbon 2+ to carbon 1+ sort of thing, and it must gain an electron. It's not really doing that, but oh yeah, it's just gone half. It's just staying halfway, half colour change now. Well done. Does happen. So because you've got both oxidation and reduction going on here, you can call it a redox reaction. And you will actually find that, this is yeah. Okay, now we're going to be able to follow this, most of the time. We're going to be looking at redox. All right, if we do our definition in terms of hydrogen, okay, let's make oxygen one of them. Hydrogen is our next option. Of course, it's very easy to remove oxygen using hydrogen, isn't it? And that's sort of the reverse of the end of the electron transport chain, where you use oxygen to remove hydrogen. But you could say the hydrogen was removing the oxygen. It's both ways. So you can have your definition of oxidation or reduction involving hydrogen as another option. So this time, oxidation. How did I write it up there? Just a colon, was it? Yeah. Oxidation this time would be the loss of hydrogen. And reduction would be the gain of hydrogen. So let's see if I've got an example that will go with this. You can, just look at this as the complete reverse of the oxygen definition. And I'm going to use as an example one that we've met biologically, and that's the ethanol conversion. Now, you can do this, we know it happens, it happens biologically in the liver. We need to process ethanol, but in order to produce ethanol, it goes from pyruvate through ethanol, so we know there's a conversion there. And we know it was to do with hydrogen, don't we? Because that anaerobic part of respiration was about freeing up NAD by taking the hydrogen off and producing alcohol instead. So we know there's hydrogen involved there. But you can do it completely inorganically. There are compounds that you can use to remove hydrogen or to add hydrogen. So I'm not going to worry about how it actually happens, but if we start with our ethanol, I'll write it out properly. And our ethanol on this side, 3CHO. I will have to, in order to balance that, I will actually have to put that, but I'm going to put it in brackets because you wouldn't actually get hydrogen released as a gas, would you? but it's losing hydrogen. The ethanol, and because in chemical reactions, by convention, we only ever add stuff. So much as I would like to write CH3, CH2, OH minus H2, you don't do that. The convention is that you never do minus, you only ever do plus. So the ethanol is losing hydrogen and becoming ethanal. And so the loss of hydrogen then, going left to right, is which process? That's our oxidation, yeah? Which colour was I using? Blue for oxidation. So there to there would be oxidation. Whereas this time, of course, the reduction process would be where? Yeah, it is just it's this whole lot. You know, if you took all that and sent it back that way, then you'd have reduction going on. All right, so again, we've got the potential for oxidation and reduction to happen at the same time, but they don't with this one. It'll be one or the other, but it's still a redox reaction. Oops, let's get these in the right order. Now, obviously, not every reaction involves hydrogen or oxygen. That should be sort of, you know, something that you're thinking about. You know, we've got plenty of reactions occurring that have got no hydrogen, no oxygen, but you still get redox reactions. So this is where we then need definitions that actually involve electrons. The electron definition is the important one. So can I fit it all on here? Yes, I think I can. So this is the one that this learning outcome is really about. So yeah, electrons or electron transfer, if you like. And this is the one that's going to be most useful. It's going to be most applicable. And so what we have here is oxidation. I'm going to write it slightly differently. I don't think I had the dots in there, did I? So oxidation is the removal or the loss, and reduction is the gain of electrons. I wrote the word removal before I thought about the way that you usually remember this. But the way I remember it going back to my A-levels was oxidation is removal of electrons, O-R-E, just spelt the word or, and then reduction was the other one. But yeah, there is actually a better mnemonic, you know, a trick for remembering which is which. And it's easier to use the loss and gain for that. And it's the words oil rig. Yeah, and some of you have obviously heard that before. So for oil, oxidation is loss, reduction is gain. Oil rig. You say you've heard that at GCSE? Yeah? GCSE chemistry covering this stuff. That's good. So yeah, that sticks in your mind very easily, and it just saves you remembering. You can, you know, you can easily confuse yourself with these sort of things. So any little tricks that just set it somewhere are going to be helpful. So oxidation, something's oxidized if it loses electrons. Something is reduced if it gains electrons. And of course, those two things are going to go on side by side. All right. If we were to take an example, just quite a simple one. Yeah, I'll use the one that I've got here. If this is a fairly straightforward little reaction going on, copper oxide and magnesium metal. And if you heat those up together, you'll get copper and magnesium oxide. Now, there is a reason for that. Later on, what we'll see is that out of the two metals there, magnesium has the greater tendency to become ions. And this is what will determine whether a reaction's feasible or not. Now, the left to right reaction is feasible, and I'm sidetracking here to the end of the unit, really. But the left to right reaction is feasible because magnesium has a greater tendency to be ions than copper does. All right, so they do an exchange. And rather than having copper oxide where the copper is ions and magnesium where the magnesium is, let's say, atoms, it's a much more stable situation, if you like, to have the copper in its elemental form as atoms, let's say, and the magnesium as ions. And we'll be able to determine this. We're going to do a whole lot of little practical activities that will help us to work out an order of reactivity. And there's a whole lot of information about this that we'll refer to eventually in the red data books. But the magnesium is much more likely to be ions. So what that will mean is that the right to left reaction isn't actually feasible. All right, because the magnesium has the greater tendency to be ions. So it's not going to stop being ions just so that the copper can be. So copper oxide and magnesium will react together to produce copper and magnesium oxide, but magnesium oxide and copper won't react together. And there are other things to consider. Anyway, I'm digressing a little bit on that. So copper oxide, this is copper 2 oxide and magnesium oxide at the other side. They're both ionic, so it's ions are what we're considering. Does anything happen to the oxygen in this? Really? No. No, it stays an oxide ion. All right, so the oxygen can actually be ignored as being a spectator ion. But something happens to the copper, doesn't it? It goes from copper 2 plus here to copper nothing over there. Whereas the magnesium goes from magnesium nothing to magnesium 2 plus over there. So the oxide bit is not important. If we just look at what's happening to the metals, we can write this just as an ionic equation, ignoring the oxide ions. So oxide ions are, we describe them as spectators. All right, O2 minus goes to O2 minus, nothing happens, but metals change between, I don't want to put the word atoms. Let's put elements and ions. Oh no, the ions are still elements, aren't they? Well, I'm going to have to put atoms like that. Yeah, single quotes, and ions. Because atoms isn't the right word. Spectator ions is the right word that we use for that, but I put it in quotes. Whereas atoms means, in single quotes, means that's not actually really quite the right word, and that's a really bad little mark there. So we could rewrite as an ionic equation, just looking at what's happening here. I mustn't lose track of what I was trying to explain. Where on the left, then, our copper in the copper oxide is Cu2+. Our magnesium, however, is without a charge. And then on the other side, the copper's without a charge, but the magnesium has the charge instead. So, where is the reduction going on? What's being reduced? Sorry? Heard it. Copper, yeah. The copper's being reduced because reduction is gain of electrons. And it gains 2 electrons to cancel this out and become neutral. So that's our reduction. All right, going from 2+ to 0. All right. So, surprise, surprise, what's being oxidized? Magnesium, yeah. Oh, you're getting the hang of this. Good. So, oxidation is loss. So, it's lost 2 electrons. That leaves it with the 2+ charge on the other side. All right, if you look at this sort of the other way, then rather than what's being oxidized or reduced, what about the agents? Which is the reducing agent? The magnesium, yeah. The magnesium is the reducing agent because it reduces the copper. All right. So, what's the oxidizing agent? The copper ions. Yeah. Okay, that's probably just worth adding on the bottom. I try not to introduce those too much because of the confusion it causes. So, magnesium is the reducing agent. It reduces the copper ions, but the copper ions are an oxidizing agent because they oxidize the magnesium. All right, I can confuse myself very easily with that. Oh, what is that? Okay, now, all right, the important thing there is an oxidizing agent oxidizes something else and therefore becomes reduced. So a reducing agent reduces something else and becomes oxidized. All right, so it is confusing, but yeah, you can always refer back if you need to.